This is Wendy Pan presenting the second lab report of Physics 2211 about the motion of a falling object. So the lab is to observe the motion of an object that is dropped from rest, capture and analyze a video, and compare with the computational models, one that's considering only the gravitational force and one considering both the gravitational force and the drag force. So the physical principles that are used is still mainly the Newton's second law. The net force is equal to mass times acceleration, which is also equals to the change in momentum over time. The velocity and position update formula are also going to be used. In this lab, as the object is free-falling, the most significant force acting upon the object is going to be gravitational force, which is determined by the object's mass times the gravitational constant. In the second part of the lab, drag force is introduced to account for any resistant force the object encounters when falling. As in the first part, the observed data differs quite a bit from the computational model when we ignore the resisting force. The drag force is determined by the magnitude of velocity and the drag constant b. These are the free body diagrams. The left one illustrates if we only account gravitational force on an object. The right one, though, accounts for the additional drag force pointing in the opposite direction of falling. In both cases, the net force is pointing downwards in a negative y direction, assuming positive y is upward. The difference is the magnitude. And the key assumption in this lab is assuming there's no action in other axes or directions except in the y-axis. This is a snapshot of the tracker analysis. The points of mass of each frame are labeled manually. The graph on the right is a plot of change in y position of the pen in respect to time. The origin of the axis is set to the top of the video where the pen started to be dropped, which is its initial position. The pen's mass is 0.213 kilograms. The starting position is 000, and the initial velocity is also 000. Delta t is 1 over 30 seconds, as the frame rate is 1 over 30 frame per second, and the points of mass are labeled per frame instead of per second. The gravitational constant is 9.8 in the y direction, where we are assuming upward is positive, so that g is negative in y direction. J hat indicates the positive y direction is pointing up. B equals 0 for the first model, taking only gravitational force into account. Since the video is only 4 seconds, the code loops while t is less than 4 seconds. In a loop, both the velocity and position update formula are used as there is a net force acting upon the pen. The net force equation is also shown, which is the gravitational force formula. All the initial conditions are the same, except B is now a non-zero constant. My constant is quite big because I dropped the pen horizontally rather than vertically, so the surface area in contact is larger, and there's going to be a greater resistant force. The loop for calculation uses the same formula, except the net force now includes the drag force. Top left is the graph of y position versus time graph for only the gravitational force produced by a glue strip. And top right is the graph of y position versus time graph for considering drag force as well as the gravitational force. And the bottom is the graph comparing the computational models and the actual experimental data. We can see that the gray line, which is the model, including the drag force, matches more closely with the observed data line, which is the blue line. And in summary, both models estimate quite accurately for the beginning, starting from about 3 seconds. The first model overestimates the change in position compared to the observed data. The second model that considers the drag force matches more accurately from beginning to end. And some possible errors are putting the points of mass not at exactly the center of the pen, did not take motion in other directions into account. The ruler might be tilted, and then the camera might be tilted as well. And for the discussion question, the model that considers the drag force predicts a terminal velocity, which is the graph on the right. The terminal velocity is reached when the magnitude of the drag force equals to the magnitude of the gravitational force. With that being said, the net force is going to be 0, and a constant velocity is reached as the velocity versus time graph is leveling down. And then for the what if question, the terminal velocity would be the same, as there would be no acceleration at the time the terminal velocity was reached. The terminal velocity is only reached earlier rather than than the free falling one. And this is checked with the glow script code on the right by setting the initial velocity to be -1 meters per second in the y direction.